So, ladies and gentlemen, let's start with the first talk. The title is Densification in Classes of Involutive Commutative Residuated Lattices. Well, let me start this, this talk from the beginning. So, the paper about substructural fuzzy logics appeared a few years ago, and in the Journal of Symbolic Logic. And in fact, the basic substructural fuzzy logic is on the slide now. So there are some primitives, and there are some rules, and so on. And if in addition, well, this is called the multiplicative additive intuitionistic linear logic. And if we add further rules extending this multiplicative additive intuitionistic linear logic, then we get, for instance, the union logic. If we add that axiom, we get the involutive union logic if we add the law of double negation, and we get the involutive union logic with fixed point, denoted by this, if we add that axiom. T stands for truth and false stands for falsity in this context. And this is the logic we are mostly interested in this talk. And the first topic I'm going to speak a little is standard completeness. What does it mean? It is well known that in classical propositional logic, the two-element Boolean algebra generates the variety of Boolean algebras. So it means that a formula in classical propositional logic is true in all Boolean algebras, if and only if it is true in that single algebra. If and or stated it in another way, if you want to falsify a formula, it is enough to falsify it in, you can always falsify it in 0, 1, in that standard algebra. So it makes falsification simpler in some sense. And also in mathematical fuzzy logic, there is a related notion called standard completeness. The standard algebras in that setting are those where the universe is the 0, 1 real interval. So the truth values is a continuum of values. And there are three versions: standard completeness, finite strong standard completeness, and strong standard completeness. And this is the definition of strong standard completeness. A mathematical fuzzy logic L, or the variety, which is its equivalent algebraic counterpart, enjoys strong standard completeness if the following conditions are equivalent for each formula phi and theory T in L. The theory T implies phi, and 2 for each standard algebra, and each A model E of T, E is an A model of phi. So roughly speaking, it's the same story as the story with Boolean algebras. Well, if we confine this definition for finite theories, we get the definition of finite strong standard completeness. Whereas if T is empty, then we get the definition of standard completeness. And the starting point is this paper published 2 years ago. A few weeks ago, I would have said 1 year ago. Because in that paper, it has been proven that involutive union logic with fixed point enjoys finite, strong standard completeness. So not the strongest version, just the finite version. By the way, proving finite strong standard completeness amounts to show, for instance, that finitely generated L algebras can be embedded into standard algebras, whereas strong standard completeness amounts to show that any countable countable chain L chain can be embedded in a 0, 1 valued algebra. So the main theorem of that paper is that involutive union logic with fixed point is strongly standard complete. And the way to prove strong standard completeness has been introduced in that paper quite some time ago. And the idea is to embedding countable L chains into L chains over 0, 1 in 2 steps. The first step is called densification. Because in the first step, we embed a countable L chain into a countable and densely ordered N chain. We call an algebra densely ordered if in between any 2 elements of the algebra. There is a third one, strictly in between. And having done that, it is easy to see that, by the way, it's due to Cantor, that any countable chain is order isomorphic to the rational numbers between 0 and 1. This is the back and forth usual well-known definition. So we can kind of, if we can densify the algebra, then we can put it inside 0, 1, and then there comes a so-called Dedekind-MacNeil completion. And if it also preserves the features of the algebra, we get the embedding into a standard algebra. Most of the time, the second step is easy. So the MacNeil completion usually preserves what is to be preserved, and the difficult part is always the densification part. So how to embed an L chain, L stands for the particular logic in question, into a dense one. So what are involutive union logic with fixed point chains in this context? So those are bounded on odd involutive FLE chains, and in fact, we don't have to care about the bounds, the upper bound and the lower bound in the embedding phase, and also in the densification phase, because, well, for such an algebra, whatever it means, you will promptly see the definition. But for such algebras, if you remove the bottom and top elements, you always get a subalgebra. And it's enough to embed that subalgebra and put back the bottom and top elements in the end. So we don't have to care about the extremes. But here is the basic definition. An FLE algebra, FL stands for the full Lambeck calculus, E stands for the exchange property, the structural rule of exchange. So an FLE algebra is a structure over that signature such that it is a lattice, it is a commutative monoid, and F is an arbitrary constant, and that law is satisfied. So xy is smaller than or equal to z if and only if x arrow y, arrow is another binary operation, it's called the residue, it's greater than or equal to y. And what is the rule of the arbitrary constant f? Well, it is used to define a so-called residuation complement. It's an order reversing operation, and we call the algebra involutive if this property is satisfied. Well, an involutive FLE algebra is called odd if the residual complement operation leaves the unit element fixed. In other words, if that is satisfied, then it's called even if these two quasi-identities hold. Well, the former condition is equivalent to saying that T is F, because T prime is always F, as it is easy to see. T is the unit element, while the latest one is equivalent to saying that the truth constant is just above the false sum. There is nothing in between. So this is the algebra, especially the odd case, which we are interested in. But let me put it into a little context. Whenever I say algebra in this talk, I will always mean an odd or even involutive FLE chain. Chain means that the algebra is totally ordered. And this is the target of this talk, involutive union on EUL algebras with this fixed point. And in fact, if further you add if you further postulate cancellativity, you enter the field, you get abelian O groups, so totally ordered abelian groups. If in addition to this odd involutive FLE chain, you add odd or even involutive FLE chain, you add idempotency, then you get what are called Sugihara chains, which are algebraic semantics to a kind of relevance logic, Rm. And if you add integrality, one gets what is called involutive monoidal T-norm-based logic chains, IMTL chains. These are the closest relatives of our structure, which we are going to investigate. And if you add divisibility, you get MV chains, which stand for the famous Lukashevich logic. Well, until recently in the literature, in addition to an involutive FLE chain, either idempotency has been postulated, which is an extremely strong property and makes the study much easier, or divisibility plus integrality together. And divisibility is, again, a very strong property, and it makes the topic collapse to the very narrow, in that setting, very narrow class of MB algebras, those which are for the Lukashevich logic. And therefore, it is a kind of surprise that if instead of integrality, we add the odd or even condition, then we can characterize the structure by using abelian O groups, which are very specific structures compared to residuated lattices in general. So, by the way, if this is T, the residual complement of T is always F. And if we have the universe here, and T is here, F is here, then it's a kind of extreme situation because they coincide. Also, the even case, there is nothing in between. And if you consider the integral case, T is the top element, that's the definition, then F is the bottom element, that's the other extreme case. And in fact, that extreme case has been studied extensively in the literature, and not much is known for the case where the two constants are so close together. Well, and we are, as I said, we are going to characterize structural involutive FLE chains by using abelian O groups, and the complexity of our algebras can be comprehended by looking at the structures we represent it with. So let's move on. In 2022, that paper has appeared in Studia Logica, group representation for even and odd involutive commutative residuated chains. Let me give you briefly the details of this representation. By the way, in this paper, there is a two-phase construction. The first phase is called layer algebra decomposition. It is followed by a second stage. It doesn't matter now. But the first stage has already been applied to structurally describe finite commutative idempotent involutive residuated lattices of our algebras, the structure of locally integral involutive partially ordered monoids and semi-rings, and the fourth one, the variety of PO magmas. So this layer algebra decomposition has turned out to be a success story. It kind of fertilized the field. In fact, every odd or even involutive FLE chain can be represented a single bunch of layer groups. Let me show you, without giving you any formula, what it means. A bunch of layer groups starts with a totally ordered set. So you take any totally ordered set with least element T. So for instance, T is here, U, V, W, S. The upper we go, so this is greater than or equal to. So T is the smallest element. And for each such element, there corresponds a totally ordered abelian group. Let's denote them GT, GU, GV, and so on. So the subscript always denotes the element from the totally ordered set. And in that setting, we assume that it's a direct system, which means that from lower levels, there are homomorphisms, so ordered algebra homomorphisms to upper layers in such a way that certain transitivity property is satisfied. So the composition of this followed by that homomorphism is always this for any imaginable setting. Plus, if you remain in the same layer, then the homomorphism is always the identity. This is what is called a direct system. So what we have so far is a direct system of totally ordered abelian groups, but there will be two extras. The two extras are as follows. In fact, apart from the smallest one, all the others will be colored either yellow or green. And if it's colored yellow, it means that the corresponding totally ordered abelian group must be discretely ordered, which means that each element has its closest upper neighbor, lower neighbor. Plus, if this is the case, then the homomorphism must send neighbors to the very same element. And if it is painted green, then it means that in addition to the original group, a subgroup of it must be fixed. And the elements of the subgroups are denoted by blue dots here and red dots under there. And in this case, the homomorphisms coming from lower layers must map into the subgroup. So must map into the subgroup. It's not possible to map an element from here. For instance, this one cannot be mapped to that element because this is not in the subgroup. So it's totally ordered set, corresponding direct system, totally ordered abelian groups with those two extra properties. And well, which you can ask, if we have a bunch of layer algebras, which are the elements of the corresponding original algebra? And the elements are the elements of those, plus, for the blue ones, you copy the subgroups. You double the subgroups in some sense. For instance, these elements, that one, that are repeated here, here, here. And these elements, the red ones, are repeated here. So the subgroups are to be duplicated. And when you duplicate them, what you see here are the elements of the original algebra for which that bunch corresponds. And the second, I will not give you all the details of the back and forth construction, just one more. How to regain the order of the original algebra. Because the original algebra is a totally ordered algebra. And the way of regaining it goes like this. So, for instance, if in the direct system that element is mapped to this, then its counterpart here must also be mapped there. Plus, this is the rule. So these are those mappings, those zetas are the mappings from upward. So those are the mappings. So okay, let me do that. So let me show you two examples. For instance, this element is strictly smaller than any of its images under those homomorphisms. And in general, if they are in different layers, if the two elements are in the same layers, for instance, this is X and this is Y, then the ordering of the group determines their ordering in the algebra. And finally, if they are in different layers, then you take the one which is in a lower layer, you raise it to the upper layer, and there you compare them. See? So if this comparison is strict, then the order in the original algebra is also strict. If they are the same, however, so for instance, this is X and this is Y, or this is X or this is Y, or this is X or that is Y, so one is mapped to the other, then one of the following conditions must be satisfied. It's quite a pain to understand what it means, but once you draw them in the way I did, it becomes easy. And this is because, look, this, what I have done, I created the mirror image of this with respect to this line. And this is why it's here. Again, I created the mirror image of this with respect to this line. That's why I went there. And if I make the picture that way, then do I do that? Then it. Oops. So if I depict the elements in that way, then it can be easily seen from the picture which are smaller than the other, which element is smaller than the other, because if the mapping of it to the upper layer is strictly smaller, then the element itself is strictly smaller. And if they are the same, then the one which is where the Y coordinate is smaller will be smaller in the algebra. So for instance, this element here will be smaller than that one. So this is an easier representation because we are used to staring at two-dimensional Euclidean planes. And that understanding will help us in this densification step, And in order to embed an arbitrary odd involutive FLE chain into a densely ordered one, it is, and also it's enough to embed countable chains. It is enough to eliminate a single gap. What does it mean? It means that we take our chain to be embedded, and we must find a larger chain. Well, we start with the chain and a single gap. By a gap, I mean X and Y, such that there is nothing in between. And if I can embed into a larger chain, which eliminates, which has an element here in between, it's enough. Because since the algebra is countable, I can enumerate all the gaps in the first row. Whenever a new algebra arises, it's also countable. I enumerate the gaps, the newly created gaps in the second, and I go in that usual way. So, and every gap will be settled sooner or later. So, in some sense, so it's quite easy to see that it is enough to eliminate a single gap. So the setup is the following. We have an arbitrary odd involutive FLE chain. Its corresponding bunch representation, with this corresponding bunch representation, and two elements X and Y, which forms a gap. Well, case number one. Well, if we have that setup, it's not possible, because in this case, X and Y is not a gap. Why? Because its image here, this one, is strictly bigger than this, and strictly smaller than that. So it's settled. What if the two elements are in the same layer, which is the least element? Well, then what we are going to do, we shall add a new element in that partially ordered set called the skeleton of the algebra. And we will add that new element just above T. And we kind of Control-C, Control-V copy the algebra there with the identity. And we define the corresponding missing arrows such that it becomes a direct system in an easy way. And then what you can see that this X is strictly smaller than this X prime, which is strictly smaller than Y, because Y is met here by this identity. See? This case is closed. What if X is in a higher level, Y is in the higher level? Well, then what we do, so is this. Well, in fact, if V is not the smallest element, we can always put a new layer underneath. Or of course, if it's T, we cannot put a layer underneath because it changes the least element. Well, then the signature, the constants in the signature will not be preserved. But if this layer is not the least one, not this one, then we can always put one below. And that below will be painted green, so we have a corresponding subgroup 2. And again, we use the identity mapping, and it's easy to check that it satisfies the direct system property with the two extras, as I mentioned. And in fact, in this case, if this is X, this is Y, and this is Y prime, then since Y prime is below, Y prime is smaller than Y, but the image of Y prime is also this, so Y prime is greater than X, and that case is also closed. And what if we have that set up? If this is X, and Y is not in the layer group, but in this duplicated subgroup of it, then what we can do, we can put a layer after above this V. We get an element here. We put it to the green layer, so it will have a copy also here. And then this will be Y prime, which is again in between X and Y. And second case, what if the image of X under the homomorphism is the same as the image of Y? For instance, this is the first scenario. Then since S is not the, so if I look here, you see that the layer of Y is smaller, is greater than the layer of X, which means that this is not the least element, so you can always put a layer underneath, and then there you get Y prime, which is in between X and Y. What if X is here and Y is there? Then since, so in this setting, they are in the same layer, but one is in this copied version. Well, if the algebra is odd, then the least element is not green. So if you have something which is green, then it's not the least element. So you can put a new layer underneath, and you get Y prime according to the picture. And finally, if we have that set up, U is in a, so this is the U level, this is the V level, U, V. And, but X is not here, but in this corresponding duplicated subgroup. Then what you can do is put a layer underneath here, put it to the green section, so it will have a mirror image, at least the subgroup here, and then X prime is there, again, in between strictly X and Y. So with this functional representation, and in particular, by understanding how to draw the additional elements which came from the application, it's not that difficult to solve the, in general, very difficult densification problem. So we eliminated a single gap. And that ends my talk. Thank you very much for your attention.